computer, use this to store a number or a letter or a color or something else. That's the power the programmer themselves have at the end of the day. Other questions on representing things with bits? No? All right. So lastly then, in this middle of this black box, so to speak, is the sort of secret sauce that solves problems, that converts those inputs to outputs, those problems to solutions. So what is an algorithm? It's really just step-by-step instructions for solving some problem. And indeed, I think back to my own first time in CS50 where we learned the same from Professor Brian Kernighan. And as luck would have it, just had my 25th reunion where we pulled some video footage from 1996. And so we're actually fortunate to have the very first few minutes of CS50 over 25 years ago when I myself took it. But the lessons back then as today are fundamentally the same. And what's important indeed is to not only express yourself correctly, but precisely, as we'll explore today. This then is Professor Brian Kernighan, who years ago very memorably introduced us and my classmates to algorithms by actually in class shaving his beard. If we could dim the lights here for Brian.
The other thing that we're going to talk about in this class is the notion of an algorithm. An algorithm is a very precise description of how to do something. And the operative word there is precise. Okay, it has to be very, 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 very precise. And the task that I'm going to do is that I'm going to trim my beard, which has gotten out of whack. And I brought a variety of things which one might use to trim beards with
So suffice it to say, I don't have much of a beard, but I do have this here other technology known once upon a time as a phone book. And these phone books, of course, have lots of information in them, happen to be storing numbers and letters in particular. For those unfamiliar, they are storing humans' names from A to Z here in English, and associated with everyone's name is a number. So even if you've never had occasion to physically use this kind of device, turns out it's pretty much equivalent to the contacts or the address book app on your iOS phone or your Android phone as well. Why? Because if you pull up your contacts, of course, you see some familiar names here, alphabetized by first name or last name. And if you click on any of those names, you reach the person you're presumably trying to call or text. Pictured here then is John Harvard's, whose number here is +1 949 468 2750, which you're welcome to call or text at your leisure. But here is John Harvard that's partway through the phone book digitally. Well, it turns out that physically in the phone book, we might use an algorithm, step-by-step instructions for finding John Harvard in pretty much the same way as iOS, Android, macOS, Windows, or other operating systems themselves use. So I could, when looking for John Harvard, first name starting with J, I could start at the beginning of the phone book and start looking page by page for John Harvard. And if he's there, I can call. This is an algorithm. It's indeed step-by-step, but that was a bug. It's a few pages turned. But is this algorithm correct? Step by step, assuming I'm paying attention. So yes, like if John Harvard is in here, I will eventually find him once I get to the J section. Now, this is a little tedious. It's going to take like a while, a few dozen, few hundred pages. So maybe I could do things a little smarter from grade school, like 2, 4, 6, 8, 10, 12, 14, 16, and so forth, going twice as fast. Is that algorithm correct? So no, but why? I could miss him, right? I could just get unlucky, really with 50-50 probability, because John Harvard could be sandwiched between two pages. Now, this isn't a complete loss, this algorithm. Maybe what I could do is, if I get past the J section to like K, I could double back at least one page, just to make sure I didn't miss John Harvard. So I can still go twice as fast, plus like an extra step, just to make sure I didn't mess up. So the first algorithm might take as many pages as there are in the phone book. So if this phone book has 1,000 pages, in the worst case, if I'm not looking for John Harvard, but someone whose name starts with Z, might take me 1,000 pages to actually get there. Second algorithm, twice as fast literally. Might take me 500 plus 1 step to get there because I'm going 2 at a time, so long as I indeed fix that bug. But what we used to do back in the day, and what your phone is doing today, albeit digitally, is going roughly to the middle of the phone book, looking down and realizing, oh, I'm accidentally in the M section, so halfway through the phone book. But what do I now know about John Harvard? Is he to the left or to the right? So he's obviously to the left because J comes before M. So what I can do literally, and what your computer does figuratively, is tear the problem in half, throw half of the problem away, leaving us now with the same fundamental problem, but it's half as big. So I've gone from 1,000 pages suddenly to 500 pages. And compare this to the other two. 1,000 pages, 999, 998, versus 1,000 pages, 998, 996, 994. That's still slow. I went from 1,000 to 500 in just 1 step of this algorithm. What do I do next? I go roughly to the middle here. Oh, I went a little too far. I'm in the E section now. So is John Harvard to the left or right now? So he's to the right. So I can, again, tear the problem in half, throw the left half away, knowing now that John Harvard must alphabetically be in here. And I can divide and divide and divide and conquer this problem again and again by using that heuristic of going left or going right. And I dare say if I do this correctly, I'll eventually be left with 1 single page on which John Harvard's number actually is, or maybe he's not in the phone book at all. So how many steps maximally might that third and final algorithm take? It's not 1,000. It's not even 500 or 501. How many times can you divide 1,000 pages in half again and again and again? Roughly. 9, 10, so typically 10 times, give or take. There's a bit of rounding there because it's not a perfect power of 2, but roughly 10 times. Like, that is fundamentally better than both of the two algorithms because I go from 1,000 pages to 500 to 250 to 125 and so forth, literally having the problem again and again. So we can actually appreciate and see this even more so graphically. And this is among the things we'll do later in the term when we speak to not only writing correct code, but is your code well designed? Is it better than your previous code? Is it better than someone else's code? Is it better than some other product? If you have given more thought to the algorithms and the quality thereof, you can perhaps minimize the time required to solve problems, but no less correctly. So if we have a simple XY plot here, on the y-axis or vertical is the amount of time to solve in whatever unit of measure, seconds, pages, however you want to count. On the horizontal or x-axis is the size of the problem, measured in, for instance, numbers of pages. So this would mean 0 pages in the phone book. This would mean a lot of pages in the phone book. This would mean no time to solve. This would mean a lot of time to solve. What's the relationship then among those 3 algorithms? Well, the first one is essentially a straight line, a slope of 1. And if the phone book has n pages in it, we'll describe the slope here as essentially 1 over 1 for the algorithm with the first algorithm, turning page by page by page, which is to say, if we were to add 1 more page to the phone book next year, first algorithm is going to take 1 more step. But the second algorithm is definitely better. It's definitely faster, but it's still a straight line. So it's going to take roughly n over 2 steps on average, because you only have to go through half of the phone book because you're going 2 pages at a time, instead of the whole phone book, in the worst case, if someone's name is Z, to go through every page in total. So if we actually compare these, let me just draw some dashed lines. Suppose that you have this many pages in the phone book. If you just draw this vertical white line here, it's going to take this much time in red using the first algorithm, but it's going to literally take half as much time in yellow for the second algorithm because you're literally going 2 pages at once. But the third and final algorithm is a fundamentally different shape. It instead looks a little something like this. It looks like it's flatter and flatter and flatter. It's always increasing. It never gets perfectly flat, but it grows so much more slowly as a function of phone book size. And for those who recall their logarithms, this would be described as log base 2 of n. And in fact, that's where the math came from. Log base 2 of 1,000 is roughly 10 in total, even if you need a calculator to confirm as much. But this shape is fundamentally different. Why? Well, suppose that Cambridge, where we are, and Alston, the town across the street next year, combine their 2 phone books. And they go from 1,000 pages each to 1 phone book with 2,000 pages. The first algorithm is going to literally take twice as many steps or pages. Second algorithm is going to take half as many, or 50% more, because you're going 2 at a time. But the third algorithm is going to barely miss a beat. Why? Because if this is 1,000 pages here and 2,000 pages is over there, just inferring from the shape of the green line, it's not going to be much higher on the vertical axis than the other two were. So more specifically, if you have a 2,000-page phone book next year, how many more steps will it take you using that third and final algorithm? Just one, because you'll divide and conquer a 2,000-page phone book into a 1,000-page phone book, and then you're back at the original story. And that's the sort of power of learning algorithms. That's the power of learning computer science and learning how to program, is to be able to navigate big data, so to speak, things the size of Google, things the size of artificial intelligence training data sets, using better and better, more clever algorithms that perform faster and therefore not only make the software more competitive, but also make it more usable and more favorable for people like you and me when using that software. So when it comes to implementing algorithms as programmers, as computer scientists, what you're really doing is taking these algorithms, which might be expressed in English conceptually as we just did, but really just translating them to code, be it C or C++ or Python or R or Ruby or any number of other languages that exist in the world. But for now, let's consider how we might implement that algorithm using something that's literally still English, but pseudocode, something that is still correct, but precise and finite, as per Professor Kernahan's advice, which is to say, use your own vernacular of English and just say what you mean, but very succinctly. There's no one way to write pseudocode. It's not some formal language. I'm just going to convert the steps I did intuitively to step-by-step instructions as follows. Step 1, what I did was pretty much pick up the phone book. Step 2, what I did was pretty much open to middle of phone book for the third algorithm. Step 3, look at page. Step 4, if person is on page, then step 5, call person. If that does not prove to be the case, step 6, else if the person is earlier in the book, then open to the middle of the left half of the book, and then go back to line 3. Then, else if the person is later in the book, open to the middle of the right half of the book, and again go to line 3. Else, there's a fourth and final case. If the person, like John Harvard, is not on the page, is not earlier, is not later, what's the fourth scenario we best consider? He's just not there, else we should do something specific like quit. Now, as an aside, everyone in this room has probably had one of these stupid technical support issues where your phone or your laptop or your desktop computer just freeze all of a sudden, or maybe it spontaneously reboots for no reason. Odds are that's because not you, but some other human made a mistake. They probably wrote code working at Microsoft or Apple or Google or somewhere else, and they didn't actually anticipate that, oh, there could be a fourth scenario that could happen in the real world. But if there's no code that tells the computer what to do in that fourth and final scenario, who knows what the computer is going to do? It might by default reboot. It might by default freeze. That's just a hint of the bugs, the mistakes in software to come. But even though this is just one way to write this code, aka pseudocode, there are some salient characteristics that we'll use throughout today. One, there are these verbs, these actions. And henceforth, as aspiring computer scientists or programmers, we're going to start to call these by what more technical audience would. These are functions. A function is an action or a verb. It's like a bite-sized task that a computer can do for you. Those then are functions in this here pseudocode. But there's other types of code in here. There are these things here, if, else, else. Those are examples of what we're going to start calling conditionals. These are sort of proverbial forks in the road where maybe you go this way, maybe you go this way, but you decide which way to go based on a question. The questions that you ask are what we'll technically call Boolean expressions, named after mathematician Boole. A Boolean expression is a question with a yes or no answer, a true or false answer, a black or white answer, a 1 or 0 answer. There's two possibilities, and there's a hint of the binary underneath. A Boolean expression is going to tell you yes or no, you should go down that fork in the road. Notice what's important here is that indentation mattered as a result. Notice that on line 4, when I first asked if the person is on page, question mark, so to speak, I should only do line 5 per its indentation if the answer is yes, or true. I should only open to the middle of the left half of the book and go back to line 3 if person is instead earlier in the book. So indentation in pseudocode and in many programming languages has logical significance. It tells you whether to do things or not. But there's another construct in here, go back to, which literally makes me go back to line 3, potentially again and again and again, creating some kind of cycle or what we'll typically call a loop instead. So even in this relatively simple real-world algorithm, we have these 4 fundamental characteristics of most computer programs that we will write in this class, and you might write beyond this class, that we have some technical jargon now to describe them. But what's important to note is that line 8 and line 11, even though they're saying go back to line 3, go back to line 3, you might think you're running the risk of what we'll call an infinite loop, where you literally get stuck in a loop forever, which doesn't sound like a good thing if at some point you want to turn your computer off, even though it's still working. But these will not induce infinite loops. Why? What is happening in this particular algorithm every time we go back to line 3 that guarantees eventually we will stop going back to line 3? Exactly. If the person is on the page, we will call them or we will quit. But more importantly, because we keep dividing and conquering the problem, in this case, having the phone book, eventually we're going to run out of phone book, in which case, indeed, John Harbert is either on that page or not, and we will call or we will quit instead. So we'll see in time. And in fact, allow me to promise, odds are at some point you will write code that seems to take control of the computer for you, where it's doing something, and it literally won't respond to you anymore. That's just going to be because of a mistake, a so-called bug that you yourself will invariably have added to your code accidentally, but we'll show you ways for terminating it or breaking out of those conditions. And indeed, what we'll do in just a little bit after a break for today's lecture is explore not just these concepts, but some of the ways you can use them to solve real and very visual and audio problems. But for now, let's at least connect it to something that's been all too germane in recent months, the past few years,